Let's talk about secondary indexing. So far we have seen primary indexing and clustered indexing. We can use them only for ordered data. What if your data is not ordered? Otherwise your data is ordered but not on desired field. Then we have to go for definitely secondary indexing. Example, let's say you have primary indexing on employee ID field. Just assumption. Then data cannot be ordered on non-key field employee name, but you want to create index on employee name field also. Then definitely at that time clustering indexing will not work because further data should be ordered on employee name, but that is not the case with us. So we go for secondary indexing. In secondary indexing, so we can take, so data need not be ordered. That means I can say that our data is unordered usually. So unordered data on index field, with respect to index field I am telling. So index field. Second one. That's it. Now there are two kinds of indexing techniques are possible. Only this condition you remember. So first condition is, let's say you are creating index on key field. That is called secondary key indexing. Now if you create index on non-key field, that is called secondary non-key indexing. That's it. So simple. We'll see one by one. Let's begin with secondary key indexing. So how to create secondary key indexing we will see. Example, let's say this is your data which is located in disk in B1, B2, B3, B4 blocks. Okay. So you have 16 records and you want to index it. So what we do is we have to create index, but the problem is we can't go with primary indexing model or clustering indexing model because for that data should be ordered and we exploited that benefit, right? So that means when data is ordered we can skip lot of computations, but here we cannot do that, right? Even binary search will not work. So whenever we want, right? So what to do then? So we don't know. I will ask only one question. Do you know a particular record where it is? You have any clue? There is no clue. That is what unordered data. When your data is unordered, then any record can be anywhere. So for every record we should remember the block for that. So here I would like to tell you one more thing. Usually there are two ways we can maintain pointers. One is block pointer, second one record pointer. So what is the difference between block pointer and record pointer? I will tell you. So whenever I say block pointer, that means it points to directly block. That means you reach to the block. Now whenever you have record pointer usually, so that record pointer will have block number and record offset. I will tell you what is record offset. Record offset. Example, let's say this record, fourth record, right? In this particular block, it is fourth record. Assume that let's say all are fixed length records, then it will be easy for me to fetch fourth record. How I will tell you. Example, you will be initiating this kind of address. Let's say you want to fetch B1, 4, block number 4, fourth record. Then what can we do is, first of all, using this B1, I will go to block number 1 and that data will be transferred to your memory, main memory, right? First of all, transfer the data to main memory. So you can imagine your array, your memory as array, right? So this is array of 0, array of 1, array of 2, array of 3. So why that analogy works? Because so memory and array, everything are contiguous memory locations. So your data is contiguously stored, right? In even array also we store the data contiguously. When you store your data contiguously, then accessing it will be easy. Array supports direct access. Similarly, your memory also, main memory also supports direct access. What I want to say is, so in your main memory now, it is let's say buffer. In this buffer, so to fetch fourth record, we can directly go to fourth record when you know this address for. So finally, this entire thing will become record pointer. When these two things are given, directly I can fetch the record. I don't require to search. Understand? But usually we don't get this kind of thing. Sometimes you might not get record pointer. You might get only block pointer. Example, let's say you are searching all the records. Let's say no indexing, nothing. You want to scan all the records. Then what we will do? So definitely at that time we don't have record pointer. Directly we'll go to block number 1 and we search entire thing. Then we search. At that time you don't have record pointer available. Sometimes record pointer might be available, right? So it depends. That's why. So two kinds of pointers possible. One is block pointer, which only will because of this block pointer you will reach only block. Then for a particular record you have to search all the records. Now if you know the record pointer, record offset, then we can directly go to the particular record. Rather than searching that entire block. Understand? So that is the difference. Now I can say one more thing. Example, let's say block pointer size 18, then this record pointer size will be generally more than that. The reason you have block number and record offset. So block number is nothing but block pointer. It takes 18 plus record offset. So example, let's say in your record there are 4 positions, right? To uniquely identify them, 2 bits are enough, right? So 2 more bits are required. So here let's deal with bits. Example, block pointer is 18 bits. If you have 4 records in each block, to differentiate them we require 2 more bits, then 18 plus 2, 20 in that way. Okay, and do not worry about it. So examiner will give you what is the size of the record pointer. So we don't require to calculate. Okay, but this is the idea. Now we'll come to secondary key indexing. I am going to teach you how secondary key indexing can be created. Now what I do is I use block pointers. Using the block pointers I am going to create the secondary index. Of course you can use record pointers also, it's up to you. So let's do one thing. So far we have seen block pointers, right? We'll see record pointer now. So first of all, in my first page or first block of index, I create index for the first record. Let's say this is record number 1, okay, R1. So here I do like this. So 1, employee ID 1 is the key value. So because it is secondary key indexing, right? In secondary key indexing, so index is on key field. That's why now index is on employee ID field. Secondary key indexing I am teaching you. So first create one entry in index file, that is 1. Where is 1? So it is in block number 1 and it is a first record, right? In that way we maintain the record pointer. So rather than writing this entire thing, I say simply R1. Okay. So R1 is the record pointer of this first record. Let's use R2, this is R3, this is R4. This is, let's say, R5. So it will be simple if I use this kind of record pointer names. R9, R10, R11, R12, R13, R14, R15, R16. Okay. Otherwise you can use block pointers. If you use block pointer for particular record, again we have to search. We'll see, anything is fine, right? 1 R1, then 2, where it is 2, its address is R5, record pointer. Next one 3, where is 3? 3 is in block number 3 and its record pointer is R9 in that way. So R9 is nothing but block pointer plus offset. Fourth one, where is 4? Let's say 4 is in B4. P4 is, let's say, our number is record number is 13, right? In that way. So we write record pointers. Next, where is 5? Where is 6? Where is 7? Where is 8? We should write. Then where is 9? Where is 10? Where is 11? 12. Now we can write 13, 14, 15, 16. Their record pointers will write. For 5 record pointer is, just search, it is in R2. 6, it is R6. 7 is R10, right? Next R8, R14 in that way. Next 1, 5, 9, 13, 2, 6, 10, 14. Next I think it is R3, 9 is R3, right? Then R7, R11, R15. 13 will be R4, 14 will be, just check it out, it is R8. Next R12, R16. So these are the various record pointers. Now if I show with pointers like arrows, how it looks like, we'll see. This is 1, right? Okay, 2 in that way. Next 3, it will be like this. 4, it will be like this. In that way we can show the pointers like this, right? This is about secondary key indexing. Now a lot of students are now having this doubt, sir, the record size, your file size and your index file size are same almost, right? If that is the case, what is the fun in creating this much big index? So now you have to search here and here. Reason number 1. Reason number 1 is, at least I am now this time maintaining the ordered data, correct? I can apply binary search whenever I can, right? So when generally when we use binary search, that is one advantage. Second one, so the second advantage is, when you create index, usually the size will be not as you are thinking. That means relatively index file size will be smaller than your original file. So how can you say that? Here we are directly seeing, right? But usually this is not the case, right? Generally this is a simple table, but usually how your tables look like, I will tell you. In the reality, your tables will have thousands of columns. So when you have thousands of columns, then they look like this: column 1, column 2, column 3. This is your file structure, thousands of columns. So when you have thousands of columns, obviously the effectively this file size will be bigger than this index file, whereas in your index you have after all 2 columns, right? That is one difference. Second thing, so there might be some columns in your file, original file, they will be binary large objects like image files, video files. If it is image file or video file, so that might take a lot of space, like megabytes and kilobytes. But your index doesn't have binary large objects. After all, your index always will have what is key and what is record pointer or block pointer. If that is the case, then relatively your index file size will be reduced. That is one thing. Now after that, I am going to teach you one important aspect here, one more important idea, that is multi-level indexing. In multi-level indexing, what I am going to do is, so I am going to create index on index. That means this is index, right? So I treat this as again file, and I am going to create one more index. Yes, we can create index on anything. This time at least we have advantage that it is ordered file. Then I can go for primary indexing, because your data is ordered on key field. So we can go for primary indexing, and I can reduce the size of the index again. If it is again, it is not reduced, again I can go for one more level of indexing, that is called multi-level indexing concept. We will see soon. Okay, at this moment let me focus on this secondary key indexing. I finished it, right? So finally I want to say that though you are looking, it is looking like original file and your this index file looks same, but that is not the case because of the two reasons. One is binary large objects. Second one, number of fields in your original file may be hundreds and thousands, right? So that is one reason. They are the two reasons. Now in the exam they might ask numerical questions here, like they give complete data. That's it. You remember this picture. This is the index. Example, I want to search using this index. How I do, I will tell you. Example, you are searching for a record called 14. First of all, this is ordered data, right? Whenever it is ordered data, then go for binary search. Using the binary search on the pages, these are all pages, right? So using the page concept, so we can apply the binary search and we can find out the right block where your data resides. Example, for 14, then you will come here and you will end up your search. Once you get it, then take the record pointer and directly go and take it. We know that it is a key field is I can say candidate key or primary key. That means no duplicates, then only one record. If you search, if you get this record, that would be fine. Now especially let me focus on this particular index, that is secondary key indexing. Don't worry about multi-level indexing, later we see. I would like to ask some questions, that is, what are the things usually people do, user do. Example, someone creates a table, let's say this kind of thing. What are the things he will do on the table? Already I told you the major operations people do is they scan the table, and probably sometimes they insert some data and they delete some data, right? So insert, delete, scan, and range queries they do, right? So range query, and one more, let's say scan, insert, delete, range query. One more thing is search with equality. So they might search with equality, like where employee ID equal to 100, that is search with equality. For this, so we will see the time complexity. This time we don't go with rigorous analysis, just we see the number of block transfers, that is more than sufficient. Example, scan. How to scan? Simple. To scan, if you really are using index, then go to first one, because you are scanning, scan the index like this. 1, go to R1, fetch it. 2, go to R5 and fetch. There is no advantage of index. Rather than doing this one directly, I can do that on my file, correct? But really if you are using it, let's say really your query optimizer uses it by mistake, then what happens? The time complexity will be, so how many blocks will be transferred? All these blocks will be transferred, correct? Example, there are B blocks, then each block transfer time D, then it would be B into D plus we have to access these blocks also, right? So if really, so how many blocks we have? We don't know, right? Number of blocks, let's say something, we assume that for this problem especially, number of blocks same, right? Here also again one more thing, B into D. So index blocks into D and original file blocks into D. If I say B1 here and B2 here, it would be more convenient, right? So if you have B1 blocks in your original file and B2 blocks in your index file, we have to search all the B2 pages, and data transfer time or disk transfer time is B2D and this is B1D. You know that formulas, right? Similarly, insert. How to insert? See, there is a danger here. To insert, because it is ordered data, first of all we have to insert in the original file. Since it is not ordered data, happily, so we can insert anywhere into new page, correct? So that won't take much time. Create a new page because already your pages are full. So page and block are same. So B5, create a new block B5 and write the new data. Example, you are inserting something 17 comma K. Happily we can write it within one block transfer or two block transfers, right? So not a problem, one or two doesn't matter for us. That's good for me. But we have to update in the index. Where to update it? It depends. Example, this data is something called, it is in between, like 10.5. Though employee IDs cannot be 10.5 everything, we're simply, just for our convenience, let's assume that, let's say your value is 10.5. If it is 10.5, then we have to keep the 10.5 here. Then we have to move all the records, right? So it takes a lot of time. Just we are seeing the issues, right? So that is the idea about insertion. Okay, we don't see the values. Now deletion. So how to do deletion in the file? How you delete? Already I told you how to delete, right? So did you remember whenever some data is deleted? So I explained you that organization, right? How your block will be organized. Otherwise, how your page will be generally organized. There will be some, whenever data is deleted, so this will be added to the free records, right? So we have seen that. Please refer my videos. Okay. So how to organize your file? That means with fixed length records. Already I explained you. Just go through that. Now, so this is about delete, right? Simply, so delete somewhere and that's it. After that, we update this index. We have to delete in the index also. That might take some time, right? So it looks like secondary key indexing taking a lot of time, correct? That's why it's not so good. But range query, example, you have range query. So whenever you have range query, what to do? Example, your query is like this, where employee ID greater than or equal to 30. Then go for a record with 30 first. Apply binary search and search for 30. Otherwise, let's take a value which belongs to our set, like 10. Example, you are searching for all the records which are greater than or equal to 10. How you do it? First of all, go for 10 in the index. Yes, I will get it through binary search. Quickly I will find out, and let's say record pointer is R7. I will go to R7. But if you get it, what about other things like greater than or equal to 10 means 11, 12, 13, 14, whatever, right? But there is no clue. We don't know where they are. If your data is ordered, I can say that after 10 I will get 11, 12, 13, 14. So that kind of facility now we don't have, right? So again, it's not so great. What we do is we just understand good or bad or not so great. So we'll use that words. Scanning. Whatever the index you use, scanning takes all the file access, right? But here you are accessing index file plus overall file. Not so good. Now insert. Insertion, usually for that we have to go to the file. Happily we can insert within one block transfer or two block transfer. There is no problem. But we have to adjust this index. It takes a lot of time, correct? So that's a problem. So insertions, deletions. How to delete? Delete a record. But whenever you delete again, we have to adjust here. That's a big deal again, right? So now range query. For range query, so example, employee ID greater than or equal to 10. I search for 10, I got it. But there is no other clue for other records which are greater than 10. Again, we have to search for 11, 12. So I don't know, right? That's why the only thing we can do for range query is start here. Best thing is go to the file, scan entire file. That is the best thing. Whenever you see a record which satisfies the condition, take it. Indexing will not help you, right? So that is a problem with secondary key indexing. Range queries are not so efficient. Now we'll see search with equality. Example, you are searching with equality. It would be easy. Just apply binary search here. You will get the value. Example, employee ID equal to 10. Then go to happily 10 here. You get R7. Just fetch it, right? So at least this is better, correct? if you compare with other things. So this is all about, secondary indexing. So we are, covering all the things which are required for GATE. I mean, I'm covering more than that, just believe. So you just understand the concept and issues. Okay. So there will be some things, which you may not understand very clearly. If you apply a thought, that means, spend some time on your own and think about it, like, try to interpret them. There are some students, they don't interpret, they don't imagine, and they don't ask themselves questions, then they can't understand. That's why, so whatever I teach, just try to understand them, and you have any questions or anything, please post that questions on, forum, so that I can answer. Because, whenever there is a concept, so 100% no one can understand. If you are understanding 100% means you are not understanding anything, you are not really understanding. So the understanding process will have a lot of doubts. Example, it's a real student, some student is understanding something, then in that process he will have lot of questions. So whenever you are getting lot of questions, you are understanding something. So that is important. Ask yourself. You should not be a blind follower. If you blindly follow whatever someone says, then that will not help you, right? If I do something wrong, you just follow it. If I do something correct, then you just follow it. But you should be a person, you should be such a person, so that you should ask a lot of questions to you, and you should get lot of questions here. Do we have any alternative? What is the problem? I mean, can we have any different indexing? Everything. Okay. So now in GATE exam, they ask fundamental questions. I will tell you what are that. They ask one mathematical question here. What is the file size of secondary index? That kind of very easy question they ask. We will see one question now. Let's read this question. Consider a file of size 2 power 40 bytes. Block size is 4096 bytes. Record size is 150 bytes and key size 10 bytes. Record pointer size is 22 bytes. The number of blocks required to store the file if unspanned organization is used. So what is unspanned and unspanned, we will see first of all. Example, this is your, let's say, block. In that, for simplicity, we assume that, let's say, you have 10 bytes of space, only 10 bytes. Record size, let's say R, mod R is, let's say, something 4. Then how many records you can keep? Record number 1, 4 bytes. Record number 2, 4 bytes, 8 bytes. Now there is some space which is 2 bytes. So no record can fit here. So what we do is, so we write the record number 3, some part of record 3 here, some part of record 3 here. So this is called one organization, that is spanned organization. There is another organization that is unspanned. In that, what we do is, rather than doing that, we leave that space. So only we write record number 1, record number 2, then there will be empty space, we leave it and we don't worry about it, and new record starts here, R3. So we write some special information like this. So this is the end of the records. Something we can write we can write some binary pattern to say that this is a unused space. That means not a proper data. So we can do it, not a problem. R3, R4. After that, still there is a space here, right? In that way, everywhere we remain, we keep some space because we can't go for span organization. What is the problem with span? Generally, whenever it's span organization, two things. Your address calculations will be difficult. See, so far if it is span, if the number of records are fixed in every block, it will be easy. I can say that this is first record, this is second record, this is third record. Address calculation, calculating the address of the first record or second record would be easy. But in span organization, it is very difficult to find out the first record address, second record address, because we don't know. Example, when it is spanned, see, here first record, it's fine. It is starting from maybe example record size 4, then it will occupy 0 to 3 bytes, 0, 1 to 3. Then easily I can say where is second record. But in this process, see, this R3 in the second block takes only 2 bytes. Remaining records R4, R5 takes 4 bytes. So address calculations will be difficult for accessing the record, right? So to search, example, you want to access R5. For that I have to start here and I have to linearly search all the records. That's why it's not good. Usually unspanned organization is better, but it wastes lot of space. We should take care of that two things. Really you are not wasting lot of space, better go for unspanned organization. In unspanned organization, so it's very easy for me. Example, I have a block and some records, and record 1, record 2, record 3. If I know the record size, example 4 bytes, then I know where is each record, right? Example, you want second record, I can apply the formula. Example, this is starting address of this block. Example, this is starting address is 100 something, assume. Otherwise, let's take 0. Then if you want first record, it will be 0 to 3. Second record, 4 to 7 in that way. Third record will be 8 to 11 in that way. Every record can be accessed with simple value, right? Example, you want third record, 0 plus how many records to be passed? 2, right? 2 into each record size 4. 2 4s are 8. Then it starts at 8. In that way, every record can be indexed directly. But in span organization, we have to traverse all the records to find out the right record. So these are all technical details. If you don't understand, you should go through data structures and algorithms one more time. Now we'll come to this one. In this one, so far there are two problems now. One is unspanned organization, second one spanned organization. How it affects our calculations, we'll see. First of all, this is your block, right? What is the size of it? 4096 bytes. Now what is record size? 150 bytes. We'll see whether this number of records will perfectly fit in the block or not. Let's divide by 150. It is not properly divisible. Let's see what happens. 153 is sorry. So what we do is 4 plus 9 13, 13 plus 6 19. It is not divisible by 3 also. 275 is a 150. It is 2048. Now 75 2 plus 4. So what we do is 75 to the 150. So still we have 54, 548, 76, 548 means I think it is something around 7. 75 7s are 7 5 is 35, 3 7 7 is 49, 52, 525. But I have how much? 75 to the 150, 54 I have. 54 548 but 525, then still you have 23 I think. Okay, so 23 means it will become 230, then it will be 27.3. that means 27 records you can happily keep here. Okay, 27 records, and there will be some unused space. First of all, because we are seeing unspanned organization, so this space will be wasted. How much space will be wasted, I will tell you. Since only you are keeping 27 records, just multiply 27 into 150. What you get? So 15 7 is a 105. So 105. Otherwise, I do like this. 15 7 is a 105 10. 15 2 is a 30. 30 plus 10 40. 405 0. So 4050 space will be used. 46 will be unused. Okay. So finally, this 46 is waste. What is effectively the block size? I can say, since you are using only 4050 space, I can say that the block size effectively you are using only 4050, right? Now let's go to the calculations. The number of blocks required to store the file if unspanned organization is used. So now how many records we have? Not mentioned, but file size is given. Whenever file size is given 2 to the power of 40 bytes, okay, now, and block capacity is now effectively only 4050. If I divide by block capacity, then we will find out the number of blocks. Why, sir? Example, let's say you have exactly 8100 bytes. Your block capacity is 4050. Then how many such blocks are required? For 8100 is nothing but 2 times 4050. That means 2 such blocks are required. So that means 8100 by 4050 would give that answer. That means finally what we have to do is we have to divide the file size by block size, effective block size, because it is unspanned organization. We are wasting the space. We should not consider that. So if I don't consider it, answer would be 2 to the power of 40 bytes by effective file size 4050. Okay. So if I simplify, whatever I get doesn't matter. You get something here, 2 power 40 by 4050 is the answer. Remember it. First one. Now we'll go to spanned organization. In the spanned organization, we are not wasting any space, correct? So we are using all the space. Then it is like complete block size you are utilizing. So what is the file size? 2 power 40 bytes. So now what I am realizing is this formula is giving you answers easily, right? Take the file size and divide by block size, you get number of blocks. That is easy from now onwards. What is the block size? But only thing is now from now onwards, for unspanned, we should write effective block size, how much block size you are using in each block, and in spanned, complete block size. What is that? 4096. So this would be the answer for the second one. I think there might not be any much difference, right? Because 2 power 40 by 4050 4096, maybe one or two blocks difference, otherwise some 10-15 blocks difference you get. Okay, so this is about this problem and calculations. Now we'll see one more problem, Q3. The number of blocks required to store index if secondary key indexing is used and file organization is unspanned. So here, since record pointer is given, we should assume that in your index we are storing key comma record pointer rather than block pointer. So let's follow that concept. So in that file organization is unspanned. So let's see the structure of your block. What is block? Block size 4096 bytes. Out of 4096 bytes, now we'll see how much effective block size you are using, because in unspanned organization some unused space will be there most of the times, right? It depends on this divisibility. So what is the record size here? Because it is index now, what is index structure? Key field comma record pointer. Since key field is 10 bytes, record pointer is 22 bytes. So here records are, in my index file, records are of 32 bytes long. So now let me divide block size by record size, then you get number of records we can store in a block. Since 32 can divide for 4096, then I say 2 power 12 by, it will be 2 power 5, it would be 2 power 7. So there are 128 records in each block. So whether it is unspanned or not spanned now doesn't matter, because unspanned is not wasting the space, spanned also, definitely spanned cannot waste the space, right? Finally it is like, so total block size we should use in the calculation, that's it. Now total block size. Now come to our problem. So how many blocks are required? That is a question to store index. First of all, ask yourself how many entries will be there in your index. So recall the concept. Each entry represents one record in the original file. Since the number of records in your original file is 2 to the power of 40, it is bytes 2 to the power of 40 by, what is the record size? 150 bytes. If I divide your original file size by record size, you get number of records. That is simple aptitude question, correct? So 2 power 40 by 150 is the answer, number of records. So for every record here there is an entry, that is a secondary key indexing principle. So but index record size is here different, that is just now we have seen 32 bytes. Now the question number 1, what is the size of index? Simple, number of entries into each entry size. So 2 to the power of 40 by 150 is number of entries, correct? Just now we have seen, into record size 32 bytes. So these many bytes. So that would be the answer, 2 power 40 by 150 into 32 bytes, whatever. Now the question, let's say number of blocks, not file size, correct? So given a file size, now you have a file size of your index. What is the what are the total number of blocks required? Simple, divide by block size. So effective block size, since it is that 4096 is divisible by this your files record size, then effective block size is 4096. Otherwise we would have got like 4050 if you have some unused space. So that doesn't affect your problem. So finally 2 power 40 by 150 into 32 by 4096. Answer is 2 power 40 into 32 by 150 into 4096, whatever it is. So this is the index file size in blocks. The next concept is secondary non-key indexing. We will see. So it is like same secondary key indexing. The only difference is now index on non-key and data is unordered on non-key field. See here example of non-key field is employee name. So your employee name is this one and it is not unordered, you see A, B, C, C, A, C, B, D, correct? So in unordered data, how to create the index? Very simple idea. So again, we don't know which record is positioned at which place, right? Then we what we do is we create index for every entry, otherwise every record of your original file. So this is, let's say, record number 1, this is record 2, this is record 3, this is record 4, and record 5, record 6, record 7, record 8. Okay, these are all record pointers. So I remember them. First of all, 1, sorry, because we are creating index on employee name, that's why key field is employee name. So first record A, where is A? So A is in what is the address? R1, right? Okay, of course block number 1, but specific address is R1. Now in block number 1, so in block number 3 there is one more A, right, which is R5 in that way. So here rather than maintaining one record pointer, we can't maintain one record pointer because you get multiple record pointers. So this is one alternative idea. So employee name record pointers A R1 comma R5. Second, B. Where is B? B is in B1, record pointer is R2 and another record pointer of B is R7. So there are two records with B. Next, so we'll go to another page. I am assuming this page is full. So next, C. C is R3, R4 and there is a record with, so here we have to use variable length record. So it would be R3, R4 and R6. Next, D. D is in only R8 in that way. So we create the index. Now, sir, how to access? Simple. Example, you are searching for A. Come here first of all. So here now, since it is ordered data, index is ordered data, we can apply binary search to find out the record value. Key value. So here it is A, right? Then whenever you reach here, then first of all take R1 and go to record, directly go to this block and fetch it. Then R5, directly it will point to this one. I can show like this. R1 points like this and R5 points to like this, right? A particular record. We can access it. So this is a way usually we do it. But however, my question is, we can't directly go to the secondary memory, right? So though you have record pointer, we have to consult disk space manager. My dear disk space manager, I have record address, please give it. So in record pointer, however, you will have a block address and record offset, we know that. So your disk space manager will see the block number and that block will be first of all transferred to your main memory. After that, in that main memory, since you have a record offset, example this is 3, that means third record, then we will directly index into third record. Here one, since I am assuming that let's say these are all fixed length records, so we can do it, not a problem. So if it is variable length record, then rather than maintaining record pointer, we maintain block pointer and we search over there. So it depends. So we don't require that many details. You can understand them. Ask yourself a lot of questions like what are the other alternatives we can have. So now we understand that this is the concept of secondary non-key indexing. Very simple idea. But here you are maintaining variable length records. To avoid that, if you want to have fixed length records, then what to do? So we have an alternative strategy. I will show that. Now we'll say alternative strategy. Rather than maintaining variable length records, we maintain fixed length records. So usually maintaining variable length records takes lot of time. Second one, it's little bit complex. So you can easily understand, given a page, if you have variable length records, accessing them would be difficult, right? And placing them also will be different. So that's why, most of the times we try to keep our records in a fixed length fashion. That's why. Then how to do, I will tell you. In the first level, what you do is, so do like this. For every record, for every different type of employee name, example A, right? So only keep an entry point here. So I am going to create a new block. B1, B2, B3, B4, right? So create a new block specially for this B5. So the purpose of B5 is to hold all the block pointers where A resides. So that's why A is starting pointer is B5. In B5 I write all the block pointers like this. What is the first block pointer? Otherwise I maintain record pointer. For A, one record is R1. What is the second record pointer? R5 in that way. Next, after R5 anything else? No. So R1 is linked to R5, of course. So we scan like this. First of all R1, after that R5, in that way we take it. So here B5 points like this, right? Second one. So what is the next record? B, right? So what is the starting entry? For that I create a new block. Okay. For B, so where it is in two places, right? I remember. So for that B6. So in this B6 I write like this. So record pointers of B. What are the record pointers of B? Record pointers of B are R2 comma second one R7. In that way I hold all the record pointers in one block. So this points here. Similarly we can go for next record. Let's say that is C, correct? Then we have D. So C starting pointer, let's say, is block 7 and D starting pointer is block 8 in that way. So B7 is a collection of record pointers of C. What are the record pointers of C? One is R3, second one R4, after that R5, right? So sorry, R6, R3, R4, R6, R3, R4, R6 in that way. And the entry point is B7. So like this. Now D is pointing to B8, of course. So we are going to write here B8. In B8 we write all the collection of D records. D only one, right? Then here we write R8. So the advantage is later, example, let's say new record is added, something like anything. So let me add here one new record, that is in the file something 9 comma something A. What you do is directly come to this index, search for A. So A's entry is B5, right? In this one, after R1, after that R5, we write this one. Let's say it's record pointer something R9, then we add R9. So adding and deleting is quite easy here, right? So this is the idea about secondary non-key indexing and second alternative strategy. Either we can use first alternative or otherwise second alternative. So we don't have much worry about it. But in the GATE exam, they can't ask questions related to this one because it is a complex structure. If it is simple structure, they can frame easy questions. Otherwise, they can't frame questions, right? That is one thing you remember. That's why there is no GATE question from this one. But remember this concept. This is the way usually secondary non-key indexing will be prepared. If you understand that, you can answer any question related to GATE. Don't worry. Okay.